Here's another example of a nucleophilic addition reaction with a weak nucleophile. Right, so this requires a catalyst to make it work better. We've seen there's an example of reaction with water, which requires some HCl. Alcohols can react very similar to water, and they are weak nucleophiles, and they can do the same sort of reactions. But rather than doing a hydrate, here in this case, reacting with alcohol and HCl is going to make what we call an acetal. Right? You'll notice it's the key difference between it and a hydrate is some sort of R group, so carbons bonded to the oxygen coming from the original alcohol, rather than just having a hydroxide in this case. So this is one of my favorite mechanisms because it's super long, but not really that complicated. So there's a lot of steps. Hopefully I'm not drawing them too small, but we'll take a look, and I think they're all pretty reasonable. So any alcohol mixed with a little bit of catalytic HCl, I should write that. Right, that's going to have a protonated alcohol, maybe less used to seeing this than H3O+, but it's the alcohol version of H3O+. Right, so think of it like that. And what's going to happen? Well, where is the strong acid going to react with here? There's really nothing to react with but the lone pair here. So we'll do a proton transfer that activates the carbonyl, so then it can react with weak nucleophiles. Okay, so now that my carbonyl is activated, I can do my nucleophilic addition step. Right, so alcohol will add to that carbon, pushing the electrons up, giving me an alcohol. We don't have an alcohol in the end, so we know that's going to have to change, but we're still following the same mechanism as we're used to, and the same mechanism from the hydration. Proton transfer to activate, then do nucleophilic addition. Oops. So at this point, if our alcohol is added here and attached to this carbon, push the pi electrons up, so now we have an alcohol. But that whole alcohol, again, is unstable. It's got an extra proton, so it's going to give that up to another alcohol. Right? This reaction would generally be done probably with the alcohol as the solvent. So left side, I still have my OH group. Right side, that looks like an ether. A proton transferred back into the solvent, right? So the acid goes back to another alcohol. In this case, at this point, which is a midway point in the reaction, this functional group has its own name as a hemi acetal, so halfway acetal essentially. And this is the same set of mechanistic steps that we saw for the hydration reaction, but notably we can put two carbon groups on there, and notably we have other positions where that proton could add, right? So we could put a proton back on this oxygen here. That would put us back, right? And this reaction is in fact in equilibrium, so that could happen. But I could also proton transfer to this alcohol. We've done that before as well, right? Again, it's a long series of steps, but nothing that we haven't seen in other mechanisms before. Having an acid protonate an alcohol is not so unusual. And in fact, that's how we're going to get rid of it in order to make this reaction work. Right? So when we protonate an alcohol, that makes it a good leaving group, right? So we have a good leaving group now. We can do a heterolysis step, right? Water is a very good leaving group. Water can come off, in this case, making a carbocation for a coordination step where that alcohol is going to add. Right now we're almost to the way there. I've attached one alcohol to the carbon. Now I'm doing a coordination step to attach the second. I hope I left myself enough room here. I didn't. Right, so if my alcohol adds to this carbon, the whole alcohol is going to add, then it's going to need yet another proton transfer. Right, so giving that proton back to the alcohol again, we said it was a catalytic acid, so that makes sense. We're giving it back one more time. Going into the third row here. Forgive me. And so what have I got left, right? So when I got to my hemiacetal, I've added that first alcohol sort of ether group here, so that's still there. Then the second ethanol that added, I've just taken the proton off, so make kind of a funky face looking thing here. And we've got the protonated alcohol back in the end, kind of make a little dividing line here for all the different steps. So yeah, from reactants, 1, 2, 3, 4, 5, 6 intermediates until we get to the product. Yeah, that's a lot of steps, but let's take a look at it, right? So there's a lot there, a lot of oxygens, a lot of squiggly lines, right? We should put this up on the board to impress our friends. But what have we really done? Done proton transfer. We've done a lot of those. Almost all of our mechanisms have that. Our new for this chapter is nucleophilic addition. Right? Another proton transfer then. Another proton transfer, right, to get to the hemiacetal, right? Our good leaving group water comes off. That is a heterolysis step, followed by a coordination. Right, so these two steps here combined are an SN1 reaction. So proton transfer, nucleophilic addition, proton transfer, SN1. And SN1s with alcohols and weak nucleophiles usually require another proton transfer. Right, so there's a lot of steps here. It's starting to look like an enzyme reaction, but this is our nucleophilic addition to polar pi bonds, a way to make a or to make a full acetal, starting with a hemi and then keep going, making an acetal here. Thanks for sticking with me.